Before we discuss surface integrals of vector fields, we need to understand that the surfaces must be two-sided or orientable. Now, at any point on an open surface, there could be two normal vectors. Either we could have a normal vector going upward, or we could have the normal vector going downward. Okay, so now if it's two-sided, we can determine the direction of the normal vector, and that makes it oriented. Okay, so the orientation or direction of the normal vector must be determined. Now we're going to use the convention that if we have a closed surface, so it's something totally enclosed, as in this example, that normal vectors will always be pointing outward. So closed surfaces, the convention will be that the normal vectors point outward. If it's a two-sided surface like this where it's not closed, then we must determine which direction is the normal that we're considering. Do we want the normal to be upward or to be downward? Okay, so the most common surface integral of a vector field is called a flux integral. So what we're going to be looking at is we're looking at movement, due to a vector field through the surface. So it's going to be going normal to the surface. And so that's why we're interested in just the flux integral. So the notation for that is this double integral of f dot n ds, or simply just f dot ds if you leave the n off. Okay, all we're doing is we're adding up the components of the vector field f that's normal to the surface at all points on that surface. So we'll be working with the flux integrals. Okay, so now, suppose we have a vector field defined as FGH, okay, and it's continuous on a vector field, it's a continuous vector field on a region in R3, and we have a smooth oriented surface. Now, we have two forms that the surface can be given as. It could be given parametrically, so R of UV, okay, in which case this vector field integral will be given as the double integral of f dot n ds. Now, our normal vector that we're going to be using is the t sub u cross t sub v, but we want it to have length 1, so our unit normal vector will look like this. Okay, because we know that t sub u cross t sub v is normal to the surface, because the tangent vectors t sub u and t sub v were tangent to the curve. So the cross product will be orthogonal to both of those. So now this will be our normal vector, and using the formula that we had previously, we'll put f dot, this normal vector. We're doing a surface integral, so that ds is magnitude of t sub u cross t sub v dA. So now notice that this magnitude will cancel, so our surface integral simply becomes f dot, that vector, that normal vector, t sub u cross t sub v. Now again, we're integrating over the region R that this surface was defined on. Okay, now if you want to go through, the t sub u is that partial derivative of R with respect to u, and t sub v is the partial of R with respect to v. Okay, so now, if the curve is given explicitly, okay, remember that normal vector, when we did the t sub u cross t sub v, or t sub x cross t sub y, and we were using an explicit definition, our normal vector came out to be minus the partial of z with respect to x, minus the partial of z with respect to y, comma 1. So that's what we're going to use for our normal vector if the surface is given explicitly. Okay, so just remember, this is what we're using for our normal vector when we're doing the flux surface integrals. Okay, so now simplifying this a little bit, this is what we're using for the normal vector. So this is going to become F dot that in. And so when you take the FGH and dot it with this vector, you come up with this. So they've got lots of forms here. I find it easier just to remember that the normal vector is this, and then I just do the F dot in each time. But when you're dealing with the vector field, you don't have to worry about the magnitude. You're actually going to use that vector, T sub u cross T sub v, with the dot product. Okay, so now let's consider the vertical vector field, F, okay, corresponding to a constant downward flow. Now I notice that there's a typo here. Just let me correct that. This should be 0, 0, minus 1, since it's downward. Okay, I want to find the flux, okay, in the downward direction, so it's orienting it for me, across the surface, which is given by this. So since we're looking for a flux across a surface, we're wanting to find a surface integral for flux of the vector field. Okay, so we're going to have the double integral, the F dot in. Now this one, they actually are giving it to us explicitly. This is the surface. Okay, and this is my F. And my normal vector will be minus z sub x minus z sub y, comma 1. Z sub x is equal to negative 2. Z sub y is equal to negative 1. So our normal vector is 2, 1, 1. Now, that's a normal vector, but what direction is that normal vector pointing? Okay, 2, 1, 1, if you were to plot that point, you would go over 2 on the x-axis, over up 1 on the y-axis, and then up 1. So you would be looking at a vector pointing upward. But we want the flux downward. So at every point, the surface here is not closed. So there is going to be a vector that's normal pointing upward and a vector that's pointing downward. So to find the downward vector, we will use negative 2, negative 1, negative 1. Now the region here that we're interested in, down that we're integrating over in the xy plane, is this triangular region. It's the shadow of that surface. So let's go ahead and see what this is going to come out to be before we start getting our limits of integration. The dot product here is 0 plus 0, 1, which since the integrand consists just of the number 1, remember that when you have just 1 in the integrand, this just gives us the area of the region. What does that region R look like? It's just going to be triangular. Let's see. The plane here intersects the y-axis. Okay, the y-axis is where we're going to have x and z equal to 0. So that would be y equal 4. And along the x-axis, that's going to be where the z and the y are both 0. So I'm going to have 4 minus 2x equal to 0. So x is going to equal to 2. So this triangle, it's a right triangle there at the origin. And we'll have length 2 here, 4 here. So the triangle has area half the base times the height, which is simply going to be 4. Now this problem, if that vector field was given us the rate of the rainfall, the mass has given us the amount of the rainfall that's hitting that roof. Okay, now let's look at another example. I want to look at the radial vector field, and I want to know, is the upward flux across the hemisphere or across the paraboloid greater? Okay, so, and it tells me to use the explicit description for the hemisphere and a parametric description for the paraboloid. So we're going to do this two different ways. So I'm going to look at the hemisphere, and then I'm going to look at the paraboloid. The hemisphere will use the explicit, and the paraboloid will use parametric. You could do either way. Just depends on which way you choose to do. Okay, so our vector field is x, y, z. And I want the upward flux. So clearly I'm talking about a surface, the hemisphere, and I want an upward flux. So I'm looking at F dot n ds, and I want to use the explicit form. So our equation of the hemisphere is x squared plus y squared plus z squared equal to 1. Okay, my vector field, F, is just x, y, z. Now I need the partial of z with respect to x. Okay, now let's take this equation and recall that when we were finding partial derivatives, I can take the derivative of this implicitly, and z sub x was equal to minus the partial of the function with respect to x over the partial with respect to z. Now, this was our function. We called this f of x, y, z. Okay, the partial of f with respect to x is 2x. Partial with respect to the z here would be 2y, 2z. So that came out to be negative x over z. Okay, also z sub y is minus the partial with respect to y over the partial with respect to z. Partial with respect to y is 2y over the partial with respect to z. Okay, so now in this form, negative the partial with respect to x will simply be x over z. The negative of the partial with respect to y will be y over z, and then 1. Okay, so find the double integral. We will have x squared over z plus y squared over z plus z. Common denominator. Now this region R that we're describing is where this hemisphere intersects the xy plane, which if you let z equal to 0, we'll have x squared plus y squared equal to 1. So we've got a unit circle for the region R. So if we want to use parametric equations, we're going to use r from 0 to 1 and theta from 0 to 2 pi. Okay, now look at this description. I've got x squared plus y squared plus z squared, but since we're talking about the hemisphere, we know that's equivalent to 1. So this is just 1 over z. But if I'm now in 2 dimensions, I need to change what z is. So I'm going to take this and solve it for z. So z would be equal to the square root of 1 minus x squared minus y squared. Now I'm going to go ahead and change this over to polar coordinates. We've got 1 over z, which is the square root of 1 minus x squared minus y squared, which is simply 1 minus r squared. And putting it in polar coordinates, I need an extra r. Okay, so now integrating with respect to r, we'll need a minus 1/2. And I've got that 1 minus r to the minus 1/2 raised the power. So it's now the square root of 1 minus r squared, and then times 2. Okay, so I'm putting in a minus 2 here to do the integration. So I need a minus 1/2 out in front. And then this thing is 1 minus r squared to the minus 1/2. So I have the minus 1/2 here. I'll have 1 minus r squared to the positive 1/2, but then divided by the 1/2, which is like times 2. Okay, so now evaluating, we'll have 0 minus 1. Okay, so we get 2 pi. So that is the upward flux across the hemisphere. Now, one thing let me point out here. When we were getting this normal vector up here, make sure that that's an upward flux. That normal is in the upward direction because the z value is 1. So if you were plotting that vector, a z value of 1 will be pointing upward. So if it hadn't been, if that had been a negative 1, you would need to take the negative of that vector for your normal vector. Okay, now let's go and look at a parametric description for a paraboloid. Okay, now I want to look at, if you look at the table that I gave previously that had a paraboloid, it was z equal to x squared plus y squared. That's a paraboloid that's opening upward. This is a paraboloid that's coming downward, starting at 1. So we've got a different equation. We can't just use the form that was in that table because that wasn't the same paraboloid. You can use the same idea, but these aren't the same paraboloid. So you have to modify it. So what I'm going to do here is I'm going to use, I need a parametric description. I'm going to go ahead and use V to be my R. And so the Z here is 1 minus x squared plus y squared. So the Z will be 1 minus r squared. Okay, and in my equation, x equal to r cosine of u, instead of theta, and y equal to r sine of u, I'm going to use the v. So I'm going to have v times cosine of u, v times sine of u, and then the z value will be 1 minus r squared. V squared, I'm sorry. So this is a parameterization using u and v. Our u, again, is our normal theta. It goes from 0 to 2 pi. And our v in this case, it's just the part for z greater than or equal to 0. And the highest point z ever has is 1. So the v would go from 0 to 1. So there's our parameterization for the paraboloid. So if we're trying to find the upward flux, we're going to be looking at this double integral of f dot n. Our f is xyz again. And our normal vector here will be the t sub u cross t sub v. So we need to figure out what that's going to look like. Okay, t sub u cross t sub v. First, t sub u will be negative v sine of u, v cosine of u, 0. T sub v will be cosine of u, sine of u, and negative 2v. The ith component will be minus 2v squared cosine of u. The jth component will be 2v squared sine of u. And the kth component will be minus v sine squared minus v cosine squared. So just minus v. So this will be the vector minus 2v squared cosine u, 2v squared sine u, negative v. Okay, so now I need to change the xyz, the vector f, to the parameters. So here's my x, my y, and my z. And now the normal vector. Look at the normal vector. We want to have the upward flux. Is this vector upward? Not with that negative v value. So to make it upward, we need to take the negative of that. Okay, and I left off a minus down here, so let's put that in. Okay, the next step we need to do is to change this vector field f to our parameters u and v. So we're going to have the x, which is this. So we'll have v cosine of u, v sine of u, 1 minus v squared, dotted with the normal vector. Now check the normal vector out. Is it in the upward direction? This minus v indicates that it's downward. So for the n, we need to take the negative of that vector. So we'll have 2v squared cosine u, 2v squared sine u, positive v. And now we'll go ahead and set the order. Let's do dv, du. Our v goes from 0 to 1, and our u goes from 0 to 2 pi. Find the dot product. we'll have 2v cubed cosine squared of u plus 2v cubed sine squared of u plus v minus v cubed these two, when you take out the 2v cubed, becomes sine squared plus cosine squared, which is 1. So this is 2v cubed, and then we still have plus v minus v cubed. So this whole thing simplifies to be v cubed plus v. Okay, so we end up getting 3/2 pi for the upward flux. So if they want to know which one gave the greater upward flux, it would be across the hemisphere. So we've got a hemisphere. Is there greater upward flux on that from this vector field or across that paraboloid? And it ends up it is across the hemisphere. And it didn't matter whether you used explicit or parametric for either of these, but since it's specified, we did it, one each way.